next part is that D. D, it is given effective load acting on conductor in kg per meter, right. Using equation 83, that W is equal to root over f square plus W Wi whole square, right. That is your W is equal to root over f square plus Wt square. F is equal to 0.81 kg per meter. We have computed this one, here it is, right. And your this Wt, we have computed 2.97 kg per meter. So then you can easily calculate W is equal to root over 0.81 square plus 2.97 square. This is 3.078 kg per meter, right. This is your D. Then E is sag in your what you call effective load. D we have computed. Now E is the sag in meter and F vertical sag in your meter. Now then it factor of safety, that term is used, right. So factor of safety is given that T is equal to actually ultimate strain divided by factor of safety. Now ultimate strain is given 12,900 kg and factor of safety is equal to 2. Therefore T will be 12,900 by 2. So this should you should keep it your mind that T is equal to ultimate strength divided by factor of safety. Therefore T will be 6,450 kg. So using equation 84, we know D is equal to W L square upon 80. So W is equal to 3.078 kg per meter, that we have calculated. L is given 150 meter and T just we have computed 6450 kg. If you substitute, D is equal to 3.078 into 150 square divided by 8 into 6450 meter. So this is actually 1.342 meter, right. This is your D. Another thing is, last one is the vertical sag in meter, right. So vertical sag we have seen earlier, it is D cos theta. So in this case F is acting this way 0.81 kg per meter, Wt is 2.97 kg per meter, resultant is 3.078 kg per meter and this angle is theta. So vertical sag will be your D cos theta. So cos theta is equal to, from here you can find out 2.97 upon 3.078. So 2.97 upon 3. So from figure 12, from this figure, right. Therefore vertical sag will be 1.342 into 2.97 upon 3.072. So it will be 1.295 meter, right. So this is the your what you call the one numerical showing part by part that how you will proceed for solving numericals, right. Next one is that location of line. So again we will come to the numerical, first little bit theories are there. Location of line. So the routing of a transmission or distribution lines requires thorough investigation, and for selecting the most desirable and practical route, following points should be considered, right. When you are designing transmission line, certain things you have to consider. One is cost of construction, 2 cost of your easements, and 3 cost of clearing and cost of maintenance, right. So all sort of things are there. Cost of clearing, it is I mean many things are there, right. So all these things just we will know, but detailed study will not go into that in this course, because it is a time bound thing. So we will just know that at undergraduate level that these are the things, right. Then sag template, right. For a for correct design and economy of your the location of structures on the your what you call, this is sag template. Although sag template is given, but sometimes this may not be exactly what you want, but some ideas you have. For correct design and economy, the location of structures on the profile with a template is very essential, right. That is sag template we call say. So sag template is a convenient device used in the design of a transmission line to determine the location and height of the structure. Sag template can be relied upon to provide the following. First thing is economic layout, minimum errors in design and layout, proper grading of structures, and prevention of excessive insulator swing, right. All these things will be there on sag template. So, generally two types of towers are used. One is the standard or straight run or intermediate tower, right. Another one the angle or anchor or tension tower. So, the straight run towers are used for straight runs and normal conditions, whereas the angle towers are designed to withstand heavy loading as compared to the standard towers, because angle towers are used in angles, terminals and other points where a large unbalanced pull may be thrown on the support. So, for standard towers, for normal or average spans, the sag and the nature of the curve, catenary or parabola, that the that the line conductor will occupy under expected your loading conditions in evaluated and plotted on template. But let me tell you one thing, for sag template all these things are given. It may not be your exactly to your design, but you have some kind of ideas, right. So, template will also show the required minimum ground clearance, that is true, by plotting a curve parallel to the conductor shape curve. I will show it later, right. And for the standard tower and same height, the tower footing line can also be plotted on the template, that also I will show you. So, tower footing line is used for locating the position of towers and minimum ground clearance is maintained throughout. So, this figure 13 shows the sag templates used for locating towers. In fact, there are no clean cut guidelines for locating the tower position, and several other alternatives may be used. This is not your mandatory thing, but other things also it can be used, right. So, for ground clearance depend on voltage level, as table 1 something is given and gives the span length and ground clearance at different voltage level. For example, suppose this is the line conductor, right, and this is your ground clearance, and this is the tower footing line. This dash line actually is the tower footing line. This is a sag template. This is tower, and this is the ground clearance, and this is the line conductor. So, sag template for locating towers. So, exact thing, your what you call, whatever you design, you may not get whatever you this thing, but you will have some kind of ideas. So, this way I have some, just to show you something, and I have drawn, this is the tower footing line. So, that will help you actually. So, and this is the line conductor, right. Assuming I mean some sag may be there, maybe they are not at the equal height or equal level. So, that is why line conductor is drawn like this, and voltage level is given, say point, that is 400 volt, 11 kV, 33 kV, 66 kV, 132 kV, 220 kV or 400 kV. Span length generally for 400 volt it will be 80 meter. This is distribution side, 11 kV also distribution side, it is 100 meter, then 33 kV is 150 to 200 meters, 66 kV span length will be 200 to 300 meters, 132 350 to 360 meters say, and 220 360 to 380 meters say, and 400 say 400 meter, and minimum ground clearance for it will be 4.6 meter, 4.6 meter, 33 kV 5.2, 66 6.3, and 132 also 6.3, and 227 meter, and 400 8.8 meter. This will be the minimum ground clearance. This is required actually. So, this is actually called your sag template, right. It should give you ground clearance, then tower footing line, all sort of things, but may not be your what you call mandatory thing, but it may help you, right. Next we will take another example, that is example 3 say. Regarding conductor vibration, little bit will come at the end. Suppose a galvanized steel tower, your tower member has original length of 22 centimeter, right, and cross sectional area 13 centimeter square, with working axial tensile load of 125 kilo Newton. The change in length was 0.2 millimeter. Calculate number 1 stress, B the strain, C modulus of elasticity, D percent elongation, E if ultimate tensile stress is 11 your what you call 1,10,000 Newton per millimeter square, determine the factor of safety. So, 5 things you have to find out. So, stress is equal to tensile load by divided by area of cross section. So, tensile load is given 125 kilo Newton. Here if I mark by reading, then this will be this thing 125 kilonewton, this is 22 centimeter, 0.2 millimeter, right. So, this one your what you call stress tensile load is given 125 kilonewton. So, 125 10 to the power 3, and area of cross section is, it is given that your 13 into 10 to the power minus 4 meter square, because it is 13 centimeter square. So, convert it to meter square. So, this will be, this is Newton and the denominator is meter square. So, this will be 9.615 into 10 to the power 4 Newton per meter square, right. Now, strain we know is equal to change in length divided by original length. So, change in length is given 2.2 millimeter, right, that means 0.02 centimeter, and divided by 22 centimeter length. So, 0.02 by 22. So, 0.909, this is the strain, right. Next is modulus of, third point is asked, that modulus of elasticity, right. So, modulus of elasticity is equal to stress upon strain, that is stress we got 9.615 10 to the power 4, and strain also we got 0.909 Newton per meter square. So, modulus of elasticity is coming 10,577.55 into 10 to the power 4 Newton per meter square. D is elongation. Elongation is equal to change in length divided by original length into 100%. So, elongation is equal to change in length was 0.02 and divided by 22 into 100. So, 0.0909 percentage, right. E, last one, the factor of safety, ultimate stress by working stress. Ultimate stress was given 1,10,000 and working stress is 9.615 into 10 to the power 4. So, factor of safety is 1.14, right. Next, we will take another example. This all this theory, whatever we have made it, it has to be supported by some good numericals, right. Now, this one, that an overhead transmission line at a river crossing is supported from two towers of height, one is 40 meter and another is 80 meter, right, above the water level, with a span of 250 meter, right. Weight of the conductor is 1.16 kg per meter and the working tension is 1800 kg. So, determine the clearance between the conductor and the water level midway between the towers. So, this is the 2 point A and B, and this is that your curve dash line is that imaginary curve, this is the point O. So, this is the midpoint, and the distance between the two tower is given 250 meter. So, this 2 point horizontal distance L is equal to here 250 meter, right, and this is the river and this is the water level, and this distance B B dash is 80 meter is given, that the that from here to here, the river level to here, it is 80 meter. This distance is D2 not given, and this from point A to the river level, it is 40 meter. Now, this from here to here A to B 250 meter, and we have taken somewhere dash line imaginary one, that is your x1, because it will, when you draw, it will come like this. So, that is why this figure should come later, but I am showing before you, before this thing, because from this problem you cannot draw this one, you have to check this condition whether it is less than 0 or not. Here it is coming, that is why it will be dash line. For example, using equation 65, x1 is equal to L by 2 minus H T upon W L. L is given 250 meter, T is given 1800 kg, H is 80 minus 40 meter, right. That is your, this D2 actually nothing but your H. So, H is equal to your 80 minus 40, so 40 meter, and W is equal to 1.16 kg per meter. That means, your x1 is equal to, right, x1 is equal to your 250 by 2 minus 40 into your 1800 divided by 1.16 into 250 W into L, that is coming minus 123.27. That is why after getting this minus only I have drawn this graph. Looking at that data, you cannot plot the graph, right, because x1 is negative. So, this imaginary line, this dash line is imaginary line, and this is the point O, right. That means, it is coming to the other side. So, where it is not existing, actually this is the two towers. So, this is not existing, right. So, that is if x1 is less than 0, that is negative, both the towers on the same side of the point of maximum sag, right. So, considering parabolic configuration, figure 14 shows the condition. This is if you consider parabolic one, this is your figure 14, right, figure 14 your this thing. So, both points are on the same side of the maximum sag, right. So, horizontal distance of midpoint P from OP dash is equal to L by 2 minus x 1, that is this is your what you call, this is O to P dash, it will be your this one, your OP dash will be L by 2 minus x 1, because x 1 is coming negative, actually it will be L by 2. If you take the real unit, it will be this total A to B is L. So, from here to here, say from this point to this point, the horizontal will be L by 2 plus x 1, as x 1 has become negative, that is why you are making like this, that OP dash is equal to L by 2 minus x 1, actually it will be 250 by 2 minus this thing, ultimately it will be added up. So, that is why it is 248.27 meters. So, this is your O to P dash, right, and horizontal distance of point B dash from, that is OB dash, that is your, this is O to B dash, this 250 is there, right. So, L minus x 1, minus we are putting because x 1 is negative, otherwise if you take the real unit, it will be L is equal to 250 and x 1 will be 123.27 meter, but anyway. So, OB dash is equal to L minus x 1 is equal to 250 minus of minus 123.27, that is 373.27 meter, right. Therefore, height of the midpoint P above O, PP dash, right. So, this is the midpoint between A and B, this is the midpoint, then what will be the this height PP dash, that is D1, what will be the PP dash, the D1, right. So, we know this, that D1 is equal to, in general formula is WL square by 2T, see equation 58, this is we are getting from your equation 58, right. So, it will be D1 is equal to W L by 2 minus x 1 whole square upon 2T, right. That means D1 that is D1 is equal to W L by 2 minus x 1 whole square upon 2T. So, that is 1.16 into L by 2 minus x 1 we have computed, that means this distance, your this is actually OP dash, this distance we have calculated 248.27 meter, right. So, it is 248.27 whole square by 2 into 1800. So, that is 19.86 meter, that is your D1. I mean, from this figure, this is the D1, this is the D1, right. And similarly, height of point B will be D2 is equal to W L minus x 1 whole square upon 2T. L minus x 1 we have computed 373.27 meter, this is the 373.27 meter we have computed, right. Therefore, your W is 1.16 into 373.27 square by 2 into 1800, that is 44.9 meter. Hence, midpoint P is D2 minus D1, right. So, this is actually D2 minus D1, that is H, right, D2 minus D1. So, midpoint P is, it is 44.9 minus 19.8, so 25.0 meter, that is below point B. So, this is your this point below point B, because D2 you got, D2 44.9 meter you have got, right, D2 the total, this is the D2, right, and then D1 you have got, this is from here to here D2, right, and D1 you have also got. So, below point B means this distance from here to here, this distance, right, D2 minus D1, that is your 20, that is below point B I am writing, that is below point B, I mean from here to here, that is D2 minus D1, right. So, height of the midpoint P with respect to A, I mean with respect, this is with respect to A, it will be your 19.86 minus 4.9, that is 14.96 meter, that is this one we just got, no, this one, just hold on, just hold on, this is just hold on, this is 65, this is x1, this is 248 meter, this 372, this is D1, and this is your 19.86 meter, this is 25.0, and height of the midpoint P with respect to A, then it will be your 19.86 minus 4.9 meter. I mean this is with respect to this point A. That means if you calculate I mean this height, I mean this one from A to this one, right. If I can make it from here to here, this point, right, it is coming actually 4.9 meter. So that is your 19.86 minus 4.9, so 14.96 meter. Actually this one to calculate this one from, say this is A, and suppose this point, some point, say, right, say it is A dash, right. So you can easily calculate that what is A dash. This will become actually 4 point your what you call 4.9 meter, this 4.9 meter. So height of the midpoint P with respect to A, that means this one, I mean if you make a horizontal line, from here, so from here to here, D1 we have got your 19.86 meter, and this one actually will become 4.9 meter. So ultimately it will become your 19.86 minus 4.9, so 14.96 meter, right. This one, this calculation one 4.9 I have not calculated here, but I ask you to make this calculation. I think I have not calculated here, right. I do not have that thing. So therefore the clearance between the conductor and the water level midway between the towers will be then 40 plus 14.96, right. So whatever, I mean this is 40, right. Look, from this is 40, that means this point also, if is A dash, this point is also say some A double dash. So it is from here to here it is 40 plus this 14.96 is coming. So 54.96 meter, or otherwise S is equal to, if you make opposite way, the total is 80, and this one you have got 25.04. So S is equal to 80 minus 54.96 meter. Even from this calculation, from this one easily you can calculate this A dash, you can easily calculate, because from the top this is your 80 meter, and your what you call, and 25.04, that is your, hence midpoint be D2 minus D1 is 25.04. Therefore your this point, that this your midway between the towers, I mean from here to here, it will be 80 minus your 25.04, that is your this height, this height, right. That means this height, right. If you subtract, then you will get your 54.96 meter, right. And as this is your from here to here, your this thing, this point is 40 from here to here. So this in your what you call, either this way you can calculate 40 plus 14.96, 54.96 meter, or from the top you can calculate 80 minus 25.04, that is also 54.96 meter. Therefore clearance between the conductor and the water level, right, midway, that means from here to here it will be 54.96 your what you call meter, right. So this is actually that how one can calculate if this kind of problem comes. But this dash line, negative line, first you have to calculate all these things, right. And this is actually from here to here, this is actually, this height is actually 40, this height is actually your this 40 meter, and this is also 40 meter, right. So anyway, so this is your what you call that for this kind of problem, that if it first you check whether x1 is negative or not, and accordingly you please do it, right. So next we will take another example. So here, that example 5, here also x1 will become negative, that is why I have made it this way. First let me read the problem. An overhead transmission line at a river crossing is supported from two towers at heights of 30 meter and 70 meter above the water level. The horizontal distance between the tower is 250 meter. If the required clearance between the conductors and the water midway between the tower is 45 meter, and if both the towers are on the same side of the point of maximum sag, find the tension in the conductor. The weight of the conductor is given 0.8 kg per meters, right. So it is we are assuming a parabolic configuration, unless and until it is mentioned, you always assume parabolic configuration, right. So, that is why assuming parabolic, if it is mentioned catenary, at that time you have to do that, otherwise it is not. So, you take L is equal to 250 meter, it is given, W 0.8 kg per meter, right, that is also given, and then H, that is difference between these two, this is 30 meter height and this is 70 meter. So, H will be 70 minus 30. So, it will be 40 meter, right, H will be 40 meter. Note that both the towers on the same side of the this thing, point of minimum sag, hence x1 less than equal less than negative 0. That it is mentioned that both the points are the one side of that minimum sag. Just now we saw the previous problem. That means automatically, even it is not mentioned, you have to assume that x1 is equal to negative, right. This is just you have to see the, if both the towers are midway between, both the towers are on the same side of the point of maximum sag. If this sentence is given, right, that means that both that means x1 is always negative. This should be in your mind when you are solving numericals, right. Therefore, from equation 61, H is equal to W by 2t x2 minus x1 square. As x1 is negative, we have seen from in the previous example that x1 plus x2 is equal to L. Therefore, x2 is equal to L minus x1. Therefore, H is equal to W by 2 and x2 is equal to L minus x1. You substitute here. So, it will be L minus x1 square minus x1 square, that is H is equal to WL upon 2t into L minus 2x1. This is equation 1, right. Now, for points A and B, that means this diagram you can easily find out for point A and point B, right, that H is equal to 40 meter. Therefore, we can write that your WL upon 2t, I mean just now we got this one, H is equal to WL upon 2t L minus 2x1. Here we will substitute all the data, right. So, it will be W is equal to 0.8 units, again I am not telling, L 250 divided by 2t, then 250 minus 2x1 is equal to 40, because L here is 250 minus 2x1, right. That means 250 minus 2x1 upon t is equal to 0.4. This is equation 2. And now for points A and P, H is equal to 45 minus 30, that is 50 meter, right. That is point A and P, because P is the anyway midway between this 2 point A and B, right. So, your A and P, so H is equal to 45 minus 30, so 50 meter, right. So, all this it is given, the between the two towers, the water midway between the tower is given 45 meter, right. So, it is 40, so therefore, points A and P, H is equal to 45 minus, between A and P, H will be 45, because it is given 45 meter, this is given 45, this thing your what you call this this one, your what you call this one, that clearance between the conductors and the water midway between the tower is 45 meter, this is given, right. Therefore, your this thing, your this is actually 45 meter, by mistake I have written 40, it is 45 meter, right. Therefore, this distance it is 45 minus 30, so 15 meter, right. So, therefore, this H is equal to again 15 meter. Now, horizontal distance between A and P, it is midway point. So, horizontal distance between A and P, it will be 250, L is equal to 250, it will be 250 by 2. Therefore, it is 125 meter. Now, again same thing, 0.8 into 125 by 2t into 125 minus 2x1 is equal to 15. This is one equation, this is another equation, right. Only thing is that you have to put L is equal to 125 and your this thing, and this H is equal to, second case it is 15. If you solve equation 2 and 3, you will get T is equal to 1250 kg, and at the same time if you solve x1, here I have written here x1 is coming minus 125 meter. So, that is why this is your, it is on the negative side, right. So, this is 125, this is your what you call the tension, right. So, with that, thank you very much. Again we will come with few more examples. Thank you very much.